Hello everyone, this is Koteshwar from IIT Delhi presenting our work titled Fruit Maturity Recognition from Agricultural, Market and Automation Perspectives. The other co-authors are Sarvesh Kumar Shukla, Samyak Jain and Sudhanshu Singh. Fruit maturity recognition is an important problem to be solved in the fruit industry. It appears at different points of the supply chain. From agricultural point of view, the farmers need to separate fruits based on the maturity level. And they don't have to deal with a variety of fruits. They grow a limited number of types of fruits. However, when we come to market perspective, we see a lot of variety. And this variety also keeps on changing depending upon the season. When we talk about automation, we also need to empower a classifier to recognize the fruit, because in automation, they need to, the robotic arm needs to pick the fruit, and this requires recognizing the fruit and also its maturity level to decide whether it should be picked or not. Now, depending upon the perspective we deal with, we can set up different machine learning setups. Now, from agriculture point of view, there is a dedicated classifier for each fruit, and its job is to take that fruit and classify it into raw or ripe. Coming to market perspective, any fruit can be supplied, any fruit image can be supplied to the classifier, and the classifier will then output whether it is a raw or ripe. Both these perspectives include binary classification, but when we look into automation perspective, since we have an additional task of recognizing the fruit, we can have various labels. One, depending upon the number of fruits we have and the maturity levels we are dealing with. So first label could be raw apple, second label could be raw orange, and then ripened apple and ripened orange. So in this way, we can have include both maturity state and the fruit type into the label, and in this way, it turns out to be a multi-class classification problem. To solve all these three types of problems, we collect several images from the internet, ensuring that there is sufficient variance across the images and the background is complicated also. So this slide presents the statistics of our dataset. Here we have total 1,600 images, and about 25% of them have been separately kept for testing our classifiers. We end up developing 10 classifiers for agricultural perspective, because 10 fruit types are there, and one each for generic classifier and one each for market perspective and automation perspective. When we are trying to develop a classifier, we have multiple options to choose from in terms of modeling. Let's say we have this set F, which comprises of possible feature extractors. When I say feature extractors, I am referring to the pre-trained networks whose activations can be used as features. And there are algorithms to which these features need to be supplied, and algorithm along with the labels, and algorithm will develop a model for us, into which if we give the features, then the model will output us what the maturity state is. Now, depending upon which element of elements of these sets we use, we can develop a model. And since many models are possible, we stack them all in this set called M, and try to analyze model by model. Each model will have its training accuracy and validation accuracy. Now we try to analyze these two accuracies to identify which is the best model. To do that, we have this objective function which has two terms, phi and psi. Phi basically captures the bias error, and psi captures variance error. The idea is to see in this term, the idea is to see how higher our training accuracy is from the minimum expected accuracy. So if this value is high, bias error will be low. And similarly, it is for capturing variance, as we know that if the difference between training and validation accuracy is low, then variance will be low. So we compare it with the maximum tolerable difference, and as a result, if this value becomes higher, it means that variance error is low. Now, using that criteria, we select the best models and show their training accuracy and cross-validation accuracy in this table for agriculture, from agricultural perspective. Here we show all possible models, and we select the best one in our from the market perspective, and using the analytical model which we have just developed. Here again, for automation perspective, we again select best model from all the possible models we have. And here you can see the accuracy, the cross-validation accuracy is decreasing. Here, let's say the accuracy was around 96% on an average, then it reduces to 95% here, and then it reduces to 88% because the complexity of the problem is increasing. Now, having selected the best model, in this table we are showing our test accuracies, and on an average, our test accuracy was 96% for specific classifiers. For generic classifiers, as you can see, it is 94.4%, and multi-class for multi-class classifier, we have 86%. So we see this trend in terms of test accuracy as well, that as the complexity is growing, the performance is decreasing. We also compare with handcrafted features, and the handcrafted features are GIST and HIST. GIST is to depict shapes, and histogram is to depict color. And as far as market perspective is concerned, it was a simple problem to classify a fruit image into raw or ripe, and color plays a prominent role. As a result, you can see that histogram plus LR works much better than GIST plus LR, because shape doesn't play a big role in determining whether it is raw or ripe. And when we combine these two features, we see very insignificant improvement. And since learned features know how to combine different features learned, and it does it efficiently, all this shape information and color information. So our accuracy happens to be much better. And then when we come to automation perspective, we see that there are two challenges to deal with. One is to identify which fruit it is, and also tell the maturity level. And we can see that when we deal with these two features independently, the accuracy is low. But when you combine them, the accuracy increases. It means that both are required to solve the dual problem which we are having. And since combination is always tricky here, and that needs to be learned, and these pre-trained networks do it in much better way, and as a result we are getting much better accuracy than even that combination. Here are some visual results which we get from agricultural perspective and from market perspective and then automation perspective. You can see from all perspectives we are able to classify. In this slide we are able to classify them well in terms of whether they are raw and ripe. And when it comes to this slide where we are showing automation perspective results, our classifier is able to correctly identify what the fruit is, and also what is the maturity level. Coming to conclusion, we try to solve this fruit maturity recognition problem from multiple perspectives, and we get high enough accuracy because we deal with pre-trained networks, and we would like to combine the handcrafted features and these learned features to improve the accuracy further, and also include more hyperparameters like layer number of the feature extractors to have more flexibility in selecting the best model. Thank you so much. Please let me know if you have any questions.